Hi, everybody. Welcome to another seminar. And today the speaker is Abbas. If you work in the network analysis, you probably know him. We had him already as a speaker, the first speaker of NetPlace, actually.
Oh, really?
But today he's going to talk about competing effect on herd immunity. And then for the discussion part, we're going to share some opinion and comments on science communication in network science. That is also the topic of our last panels in the NetSci conference. So Abbas, whenever you're ready.
Thank you. Thank you for having me. Actually, I checked that when was the last time that I was here? It was April 2022, I guess. And I checked my slides because I wanted to start from when those slides ended and continue working on that. And I also I remember a chat, I don't know if it was with Han or someone from you guys, that I was supposed to be part of the panel in the science communication, but at that time I was somewhere else, I don't know where. So just to do my contribution to you guys, I try to make some slides and say what I think may be a case. And for that purpose, I'm gonna basically try to talk from the research part less than what I should do, because I really want to spend some time over the other thing. If I know there should be a full screen. How should I make this full screen? Anyway, I guess
Try F11.
it should be fine. So let's begin with. So I'm going to talk about how different mechanisms, depending on the network structure, may compete with each other and change the picture of herd immunity. And to begin with, I should say that I spent my PhD working on networks model for epidemics. And these models are very simple in a way that they cannot be really used for forecasting epidemics, or predicting epidemics in a very practical way. You cannot use any of the models that I have been using in my research so far to say what happens next week or what intervention should be used for the new wave of Omicron or something. But they are built to give you insights. And by insight, I mean, these models capture the macroscopic dynamics and give a macroscopic picture, meaning that they are based on a lot of good approximations, but at the very end, the result that you are obtaining are just for insight. And it is a good thing to keep in mind, because at the very end of the day, when I'm talking about epidemics, people always think about COVID, and COVID is like a very complicated case. And I'm mostly interested in epidemic spreading in general. Okay, with this introduction, I am advertising my thesis, which you can find it online. I spent a lot of time to make a nice thesis. So if you're interested in this type of issues, please have a look at it. It comes with 100 pages of like explanations and then my papers at the end. I am pretty sure that all of you are even now tired of hearing about compartment models and SIR and all of these things. But anyway, I have to start with that. So to study epidemic spreading, a very standard way is to divide the population into groups or compartments and basically come up with some rate equations, which says how people move from one compartment to another. So basically we can see how susceptible people kind of get infected with this rate beta and then finally recovered with this like recovery rate gamma. And we, of course, can write differential equations and try our best to solve them. We for sure know that all of these models have no strong assumptions on the interaction pattern between the people or between agents, meaning that when I show you this as IR dynamics, there is no networks, or if there is a network, the network is like really a complete graph that everyone can technically interact with everyone else. And the idea is that if we want to improve this type of models, we should kind of see how we should solve these type of equations on them. So there are also interesting phenomena on top of these equations. For example, given the beta value and gamma value, we can see that a phase transition happen when we look at the final outbreak size. So if we run the epidemic and let it just go forever or for the time that it like saturates the fraction of population that it can basically infect, we can always see that the latest state of the epidemic can always be controlled based on the value of beta over gamma in that set of equations, which people call it the basic reproduction number. And basic reproduction number is a good measure of saying that at the early days of an epidemic, how many people get sick on average, right? So technically, this model, this simple SIR model is showing us a phase transition. And this phase transition is very interesting from the practical perspective because usually government and basically public health people would like to apply some interventions so that they keep R naught below 1 so the disease gets into its subcritical regime and finally die out, right? But the question is that when we look at the real world, there are networks, and networks kind of change people. Networks change the way that we model phenomena. And to incorporate different interventions, we should realize how their effect kind of amplifies in the network. So if we are doing vaccination, so vaccination is an intervention, we apply it on some node, but these effects kind of propagate through the whole system. And the way that our network is wired can highly amplify it or basically kills that effect. And the question is that given some sort of intervention and given some sort of network structure, how effective any of these can be. Let's think about vaccination. The question of vaccination is that always we cannot give everyone a vaccine because of so many reasons. Some people are much younger to receive it. Some people are much older to receive it. Some people don't want to receive it. Some people ideologically don't want to have it, and so many other reasons. But there is this hope or premise from old school epidemiology that if we vaccinate enough number of people, we get to something which is called herd immunity, meaning that even unprotected part of the population will be safe. And the question is how to calculate that. Like, in other words, how many people we need to vaccinate to reach herd immunity. And given the SIR framework, we can always argue that this R naught is like the number of secondary cases. So if it is below 1, we are safe. In other words, if we vaccinate pi v fraction of a population, that R naught changes to like some more effective term, which is basically 1 minus pi v times R naught. And it now incorporates the contribution of vaccination. So if now the effective reproduction number is below 1, we will be safe, meaning that the epidemic threshold will be achieved if we vaccinate 1 minus 1 over R naught fraction of a population. So if a disease is like as harsh as the reproduction number can be reported as 3, then like 1 minus 1 over 3 gives you a rough estimate of 70% of population. And it was based on this simple mean field calculation, or like this law of mass action calculation, that you basically do not think about any network structure. You just believe that a pi v fraction of people are uniformly chosen and vaccinated at random. And basically, you let everyone interact with everyone. Or even if you think about the network is a fully connected network, which we know that it is not the case for most of social networks. Social networks are sparse, they're unevenly structured, and much untrivial than what it is in this type of model. So we proposed like 2 years ago that because we had this issue with I was part of this collaboration with the Nordic countries, that it was like we had discussions with public health people that this 70% is a very bad estimate, and We wanted to show them if you add a simple layer of complexity to your calculations and to your model, then herd immunity will be not even reachable. And a simple way to think about it is that imagine you have a network, that the network has some homophily status in terms of the labels of the nodes. So we have a vaccinated population, which are more probable, which are more likely to be connected to each other, and unvaccinated part, which the situation is the same. So in network science, this is quite known phenomena, and we can quantify this feature given the degree distribution of a network through some homophily index, that when it is 1, you have like highly separated population, and when it is 0, you have fully mixed population, and when it is in negative values, it's like some sort of heterophilic, that people of some status try to be connected to people of the opposite status, right? And now imagine that we vaccinate pi fraction of people in a heterophilic, in a homophilic situation. How would the epidemic threshold would be changed? And we showed that given any network structure which follows some sort of configuration model, that we have like a tree-like structure at the back end, you will see the old formula gets scaled by 1 over 1 minus h. So when h is 0, you recover the old formula. But the thing is like that when h is positive, you get to some very dangerous phenomena, and that is if you think about some disease that the basic reproduction number is 2, then the basic reproduction number 2 with 0 homophily would give you some epidemic threshold at like 0.5 here. But if you have like larger homophily in your population, if vaccinated people are much more likely to connect it to each other than unvaccinated, you can see that you easily lose the premise of herd immunity, meaning that if herd immunity is what you're looking in a population that homophily is above some specific value, you can never reach it. And it means that you simply lose it. Like if you have network structure, everything gets very complicated, and you have to calculate everything according to your network structure. So we wrote this paper, and we showed how herd immunity in terms of the epidemic threshold changes when you have homophily and when your vaccines are imperfect, and how the epidemic size finally will be obtained. And I talk about it in much more detail in my last talk. But another way to look at the problems related to herd immunity is to look at herd immunity not after vaccination, but after natural infection. Because like in most of the cases, when we are looking at airborne disease, there is always like some sort of immunity memory that when you recovered from a disease, for a long enough time, you remain immune. So technically, if you are recovered, it is like that you are vaccinated for the next exposure. But the question is that until now, we were thinking that when a new disease come, we can vaccinate people. But with the COVID, what happened was like that it was a new virus, and we didn't have vaccines. So the only way to reach herd immunity was through natural infection. But we were not sure how safe it is or how better it can be compared to vaccination. So a lot of paper came, and they showed through very nice mathematical arguments that natural immunity, meaning immunity gained after infection to the virus, is always better than disease-induced immunity through vaccination. And the idea and the argument behind this, as you can guess, is that when we let people get the virus, usually because hubs or super spreaders are more likely to get the virus first, so they get sick first and they recovered first, and because they have a lot of connections, they kind of boost herd immunity in the network. And this was like a very nice argument because it considers the heterogeneity of networks, which was not in the previous analysis. But the problem was that it was a bit dangerous because, as you may remember, early days of COVID, for example, Sweden and UK were following this strategy that we are not going to imply that, okay, the idea was that we let people get the disease, and because of super spreading events and because of immunity of hops, we will kind of boost immunity. But in practice, it didn't happen. And for example, Sweden turned back to the typical Nordic strategy, and like they applied more intervention and blah, blah, blah. But what's wrong with these papers? Like, they're all carefully done. The problem is the assumptions behind this type of modeling. All of these models are based on networks or assumptions that takes into account the heterogeneities in number of connections. But the problem is that when you look at social networks, they are highly embedded in a space, meaning that when you look at how this is propagating in your system, is to start from some place in the network. It cannot really jump to other part of the network. It is constrained to move in space and time. And it has a very different mechanism in terms of how immunity is like induced in your system than when you're doing vaccination. When you do vaccination, you can see that you can basically immunize node at a random place. And technically, these two things are very different. And the way that your network structure is built can lead to different things. And it was our argument that for sure, when you think about degree heterogeneity, it will highly boost natural immunity, but there is a competing mechanism, and that has to do with the propagation and the constraint of the disease spread on the system, which is our network. So when you think about how disease unfold in a population, so there is always a transmission rate, let's say, and the larger it is, the larger the epidemic size it will be. And usually we have seen that there are some sort of phase transition. So below some specific value, there is no huge outbreak size. And after that, there is a monotonically increasing size, which never gets to the whole population. There are always some fraction of population left. And when a next wave of epidemic comes, like the first wave comes, some people get infected, and another wave comes with a little more transmission, a little higher transmission rate, there is another wave of epidemic. And the larger the first wave, of course, the smaller the second wave will be. But the question is that if we look at the first wave of an epidemic and look up, so I make a dictionary of people who have been infected, and then we kind of go and vaccinate the same number of people at random. So we kind of forget about the network structure between the immunized people. Then which one will lead to a smaller epidemic size in the second wave? And this figure shows you that for a triangular graph, a very boring structure that there is no degree heterogeneity, the natural immunity curve is above the vaccination curve, meaning that the epidemic size will be less in the vaccinated case, meaning that vaccination here is like more effective in terms of having herd immunity. But as I said, this is like a case that you can argue that, of course, no real network is like this, right? So we showed that if for any network structure, if you look at the first wave, so the red points, the red nodes here are those who have been infected in the first wave. So the first wave comes, bunch of people get infected, and there is this remaining part of population, which we call it the residual graph. And the residual graph has a giant component. And technically, the largest component of the residual graph is a proxy that how big at max a new wave of infection can be. And if we compare these two, like the size of the largest component of the residual graph to the size of the first infection wave, then it can give us a very nice interpretations in terms of how network structures can influence herd immunity. So let's say on the x-axis, I have the size of the first wave, and on the y-axis, I have the second wave. So of course, like second wave plus first wave is always less than 1 because we never can infect the whole population, right? And technically, direct protection would be in the shaded area. So the second wave curve is always in the white area. I mean, if it is not clear, just let me know. So the question is now that when we have different strategies, how does second wave behave in terms of the size of the first wave? Because unprotected people are here. And the question is that how much of these unprotected people will be immunized or will be kind of protected indirectly through the first wave of the epidemic or vaccination. So what happens in practice is that there is always this type of curves which deviate from the diagonal curve, and the area between this region is the indirect protection, which is actually the gain out of herd immunity, right? And usually what we want to do in most of our calculation to find this critical point. So to compare how vaccination can be different from natural immunity, what we do is that we run the first wave of epidemic on network structures that I will tell you about more. And then we remember how many people have been infected in the first wave. And we also remember more attributes of those people, like the number of connections each of them had. So one strategy is the vaccination, that we basically vaccinate the same number of people who were infected in the first wave uniformly at random. So we kind of shuffle the whole structure and we just keep the number of immune people the same. But there is another better, which is like the hope of a much better effective vaccination, is that we remember how many people were infected, but also we remember how many people they had in their immediate neighborhood. So this time we are going to vaccinate not just the same number of people, but we will find people with the same number of connection, but we just like shuffle the links. So we just ruin the spatiality or the local structures of the network, but we keep degree heterogeneity. And the question is then, natural immunity should be between these two realities, because these are two very extreme cases of inducing immunity to a population. This strategy is very famous as friendship paradox or something, you know. So when you look at this curve, for the triangular curve, you will see that the blue, which is like vaccination, random vaccination, is collapsing on this strategy, which we call it proper immunization. And it makes sense because this is like a very homogeneous network structure and the curve is below the red, right? And the reason is, of course, because there is no degree heterogeneity that the natural immunity gain from it. But when we look at networks that they have like more degree heterogeneity, so if we go from a random regular graph to an heterogeneous graph, you will see that the blue curve is not colliding on the yellow anymore, and it's like colliding on the epidemic scene, because on an heterogeneous network, everything is so randomly distributed that there is no preference that you do it by chance, that you basically vaccinate people at random or let some immunity propagate through the system. This is like too much randomness, so nothing interesting happens. But when you go to the next step, which is the case for like a more realistic case, that you have a network from a configuration model, that the tail of the degree distribution is much, much larger. Then you see that clearly the red curve is between these two optimum strategies, or like, I mean, one is optimum and one is like, of course, the worst case scenario. And this kind of is telling you the story that the Swedish people, or like most of the paper, were claiming that because like even if we make it more crazy, like the next case is the case of a network that the degree distribution is following a scale-free version. And you can always see that the red is below blue, meaning that vaccination is less effective than natural immunity. So this is what most of these papers were claiming, and it's true. And the reason is that these networks are configuration model. There is no substructure which changed the story for us. So these are low spatial networks. And when you look at the whole spectrum of the networks, you will see that these people have basically investigated this part of the networks model, like networks model who are not that much spatial. What if we come and investigate this part of the worlds of the phase of the space of networks? If we do so, like we do the same analysis, So this is a lattice, which is a highly spatial network with low degree heterogeneity. Everyone has the same. Then we have a random geometric graph. And then we have the spatial versions of the networks that we mentioned. And the real importance comes in like this part, that when you compare a network which has a heterogeneous enough degree distribution, but one has some spatial embedding, like it has more local structure, then you will see that this red curve, which was below the blue, has swapped the position of it, meaning that when you look at the spatiality of networks, then super spreaders are not the only features which kind of help herd immunity. And this was like the conclusion that when you're looking at networks, there are two, at least, hugely competing mechanism. One is coming from your degree heterogeneity and another is from your speciality, and because local things highly matter. And another thing that I'm not showing you the rest of the result because it will be very long, but another very important thing that we showed in this paper that you can now look at its first draft on arXiv is that a lot of mean field calculations cannot capture these type of specialities. And most of the analysis in epidemiology, which has usually most of the works are done by non-network scientists. And that type of mean fields never capture these things. And this is like some hope that we as network scientists can do a lot of work on improving interventions, like the effectiveness of intervention using network science toolbox. Okay, thank you. And you can see all these works on my homepage. And if you have any question, very happy to answer.
Great, thank you, Abbas. Can you hear me?
Yeah.
Yes. So as Abbas said, if some of you have question about the research part, can just ask. Sylvia, you want to go first?
Yes.
Mhm.
Can you hear me?
Yeah.
So first of all, I want to thank you, Abbas. The talk was great. Also your research, because I really appreciate the fact that you look at the spatiality dimension in all these processes. It's really, really cool. It's cool the results that you already get. What I wanted to ask you is mainly a curiosity. Are you planning to go further in the sense, are you planning to look at real spatial graphs to look at maybe some data and some like
Yeah.
Great.
Yeah, I am. Like most of my works have been just models because of so many reasons. Now that I'm going to Copenhagen, they have they have like so many good data sets. For example, they have the data which comes from the registration of people. So we know who has lived where, what school they have attended, what workplace they have been. So it gives a very nice contact data. And on top of this, there is a huge data set coming from testing. So in the Nordic countries, Denmark did the most number of testing. So on a regular basis for a long time, everyone was tested. And if they were tested positive, they would go for a PCR test. And everyone who has got a positive PCR test, the whole genetics, like the whole genome of the virus has been like sequenced. So they not only we have this contact tracing data that who has been infected by whom, we also can follow how the virus has changed, and combining these two pictures give a very nice data-oriented analysis for us. So stay tuned for next year.
Great. Looking forward.
On?
Yeah, so I'm curious, your study on the spatial network, is this entirely simulation, or you have some theoretical results for this as well?
So as you can see, we have like lines and markers. So markers are coming from like analytical type of calculations, and when we don't have them, it's just simulation. So basically, when we look at the left side, we can do everything by simulations and by very nice mathematical arguments. But for the spatial networks, there is no real useful thing so far.
Yeah, okay, because recently we have done something about percolation on a spatial network, and I really want to have something, even some theoretical insight on spatial graphs, but it seems there's not any theoretical result yet. But okay.
You should come and give a talk in our group, like at some point, like either online or on site, before I leave here. Because there are still people working on these things, and I believe that there are a lot of interesting things to look at here. Yeah, sure.
Okay, that's cool.
I have another question, which is maybe too personal, not very scientific, but did you, also you don't have to answer, but did you get tired of epidemics during the COVID time? Because I mean, I didn't work in epidemics, but I grew tired of just the omnipresence of the topic.
Yeah, I mean, yeah, for sure. There were days that, so when you are doing science, science is a slow process. So you come to office, you go home, you sink in the showers, blah, blah, blah. But in the COVID time, every random person in science was doing epidemic. So there was a huge chance that you wake up next day and what you were working was already done by some person. So like it was, you didn't need to check archive. You opened Twitter and your paper was done by someone else. And it happened to us three times. Like first a group published something and 1 week later we put it on archive, and a year after we put something on archive and then they did it after us, like 1 week later. So hopefully, I mean, fortunately, we were doing different approaches and we got same results. So we were not wrong, but it was very stressful days and I don't want to get back to it. But now that it's peacetime, I'm quite interested in it because it's a very challenging problem, both from mathematical and modeling perspective, which I am a big fan. And at the same time, it matters, you know? So those days were bad, these days are good.
Fair enough, thank you.
Yeah.
Okay. I think we can switch to the discussion part.
Okay.
Do you have a slide for that?
I have a slide. I have actually a lot of slides and what I'm going to talk about. So we have like less than half an hour or so, right?
Yeah, but it's okay. I mean,
okay, so you can see my screen, right? Okay, good.
Yeah.
So I have been involved in like science writing and science communication and all sorts of activity which relates to, I have been a high school teacher. I have taught in university. I have taught at all the levels. I have been the TA of so many different courses, and it has always been a very important thing for me, how to teach in a very engaging way. And my main motivation was all the professors that I had in university, which were really making my time a hard time at their classes. So I have spent a lot of time. I have received some awards on this, and I always wanted to talk about the way I feel about the current state of science communication in network science. What I'm going to talk now is not something that you don't know. I'm just like gathering my thoughts in a beautiful way so that I can present and then ask a lot of questions from you. So what I'm telling, I'm not teaching or telling anything new to you. I'm just like showing some slides about how I think about. So what is science communication? To me, it's like that there is always someone who knows something about some subject, but there are always people who know more about. Like when you look at hypergraphs, there is always this guy who knows more than the other one. And the guy is a good one. So he tries to let the other one learn about something in an engaging way so that this person enjoys the time spent here. And if you want to think about it, it can happen in any other disciplines. And there are always people who know more in other objects or subjects or whatever. And it's like a very human thing that there are always people who know some subjects more than others. And the question is that how well they can communicate these ideas, right? And if you are a big fan of this type of approach to science communication, it can always happen from any level of seniority or expertise to any other level, as long as it's an enjoyable process. So an expert of this level can always like let these people know, or like people at like lower levels of expertise know. So in general, the word of science communication can be interpreted as a network that we have different expertise or different subjects, and you can always let other people know depending on the knowledge and the expertise. And as you may notice, these axes are not orthogonal, because we know that in real world, sciences are not completely orthogonal on each other. This is a schematic picture, but I hope you get my point that, like, for example, when you look at physics and chemistry, they are not completely different subjects. There are parts that are completely close to each other and you can relate them. But anyway, in general, when you look at the population, there are always some expert here and people, normal people or educated people in between. And at the very end of the spectrum, there are these people who deny science, or they don't like this type of thing. And the question of science communication is that how knowledge transfers from the right to left in an engaging way. I want to insist on the engaging part, because we are people, we like stories, and we adopt them if we enjoy listening to them. So in high school, science communication is done by teachers. In grad school, it's done by university professors and lecturer. But the idea is very simple, but the practical implementation of it is different depending on what point on this axis you're going to the point on its left, right? So for example, people believe that popular science or science journalism is a term that has to do with people, meaning that when we are just like your target audience is normal people, whatever you do to convince them or tell a good story to them or like educate them can be go under this term. And of course, when we say people, people is like a vague argument. It's a very vague term. People are very diverse, and there are people who know less, people who know more because of education or because of whatever. But if you forget about popular science and science journalism, which is like a very well-defined type of approach, science communication happens at all levels. So for example, you can be Carl Sagan and make TV shows for people, and you can, for example, be George Gamow and write very nice books for people who know some mathematics or no mathematics and still learn and enjoy doing this. But at the same time, there is this issue that if everyone starts writing and telling people about science or about what they are an expert in, then it loses its meaning. So these days, there are so many people that they are participating in this process, but they are ruining it. And the reason is that because there are no expert. And by expert, it does not only mean scientifically oriented, but also social skills for letting people know. In epidemic time, there were a lot of experts that just made people scared. They were not wrong, but they were not an expert of how to tell people the stories, right? And I really like this quote from Leonard Susskind. He is like a famous theoretical physicist, and he has very nice videos and books on physics, famous as the theoretical minimum. And he says, like, when everyone is an expert, no one is an expert. So if everyone comes to TV and try to inform people, then there is something wrong. It means that my point is that science communication is something very tricky that should be done by highly skilled people. So another thing is that, okay, science communication does a good job of carrying scientific ideas from high levels to low levels in the population. So apparently science diffuses through science communication. And that is why it matters, because if we want people to know about these things, we need to come up with nice strategies to do this diffusion. So there is this model, which is called the chain model, which is a very trivial type of thinking. And it is highly supported by a lot of like community-based beliefs or ideologies that if you know something, it is your duty to let other people learn it from you. So the idea is that there is some expert here, the expert let other people who know less know, and then it goes on and it goes on and it goes on. And from now on, you can see that my arrows get like bolder or larger, and all of them have a meaning. And here, like there is this gap that as we go there, you see that the arrows are like wider, but this usually never happens like that because of so many different constraint or boundary conditions. And I will talk to you about this because this is like the whole point of my talk. When you look at mainstream science, like when you look at physics, physics is a very old science, and you can see people writing papers, writing very detailed books. The very famous one is the case of Newton. But the problem with Newton was that he wrote a very big book that normal people couldn't follow because it was hard to read. At the same time, Galileo wrote a book which was highly based on storytelling techniques between three people who are having nice time to each other and talking to each other about the sky. And then you realize that people can read it and people can kind of get the idea. So what Newton did was a huge thing for sure, but like the arrow from Newton to people was like a very short arrow. It was from expert to expert. And I believe Newton did it intentionally. He didn't want normal people to read it maybe. But Galileo, on the other hand, did the opposite. He wrote his like masterpiece in a language that people could read. And it has been a theme in science. This is a picture from Michael Faraday beginning the Christmas lectures in Royal Institute in the UK. And since then, these things are happening. So one way is, of course, that we have an expert, that the expert can basically target the people as its audience and teach them. At the same time, of course, he is an expert, so he writes paper and he develops science. So people of less expertise can, of course, gain from him. And then there is another chain of science communication happening from other people. Just keep in mind, I really love Faraday. You know, Faraday was one of those experimental physicists who didn't really know that much of mathematics. But he is such an influential guy in physics that even Albert Einstein had a picture of him on his desk. He was a guy with crazy intuition, and he was so good at letting other people learn from that and build that type of intuition, okay? Another way is that when you look at Richard Feynman is a very famous physicist that he was good in teaching science and physics to everyone. So there is a video from him teaching quantum electrodynamics. The audience, of course, is like an advanced audience. Then he has like his messenger lectures that he's basically teaching to university level people in all the fields, not physics only. And then there are his videos at BBC. So BBC made a show that he's basically telling the whole people this. So apparently Feynman can teach everyone, but is it something that any expert can do? And the answer is like a big no. And to show you why it's not the case, I'm going to review some cases that you may totally relate with. First of all, there is this famous story that even once Feynman was asked to give an explanation that why spin 1/2 particles obey Fermi-Dirac statistics, and the guy was like, okay, I will try to come up with a freshman lecture so I can tell it to everyone, but he fails in doing so. And the answer was that I cannot do it because apparently I don't understand it to a good extent. So apparently, if an expert is aiming to communicate some idea to the people, first of all, they should really have understood it. There are so many famous quotes that if you cannot explain your research to your grandma, maybe you have not understood it, or so far. Like Hilbert has this quote that if you cannot explain this theorem to the first random person you see on the street, you have not understood, or something like that. So this is like one big criteria. So you should really know what you are talking about. But at the same time, there are other skills that you need. It's not just a matter of how knowledgeable in physics or, for example, in quantum mechanics you are. The issue is that you need social skills because you're dealing with people who do not have the behaviors as a normal scientist when they face a challenge. Like we are used to struggling with new ideas. Normal people, they don't. And these social skills are most of the time gained not through any teaching. Like if people like Feynman are good at teaching, no university, no academic system has let them have them. It is their own thing. It has been either in their blood or they have worked hard to gain. To give you a very nice example, most of you may know Edward Wheaton. He is like a god in theoretical physics. He's apparently one of the greatest guy who is alive in the world of theoretical physics. And I love him. I respect him. And there was a time that he wrote this introduction to information theory. And of course, he's Edward Wheaton, so very famous. And then people invited him to give a talk over that. And when you look at that video, the video is not something that you want to watch. And then I found this, so I hope, let me know if you can't hear the video. So I guess some of you can relate with this type of behavior, that you attend a course or a lecture, and there is this guy that, yeah, as you may remember this from your early days in kindergarten, that now we have this tensor of this and blah, 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 and blah, 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 or like you are doing this integration. And apparently, a lot of us are kind of adopted that behavior and unconsciously transfer it to the next generation. So even when we get to a classroom, we always take everything by granted. But as a lecturer, your duty is to forget what you know and try to remember what people who are your audience know about this subject, right? And like, even if you look at these slides from like Edward Wheaton, like they're so boring. Of course, they're super good, but for people who are as expert as him, not like other people. Another example, which I really like, so Wired has this set of videos that they ask some expert, and they are told that, hey, you're gonna see 5 different people that each of them know different level of what you are an expert of. For example, if you're a physicist, you have to explain it to a small kid, and then someone who is in high school, then someone who has a bachelor's in physics, and someone who is a researcher in physics, and try to come up with different stories and different ways to teach them. For example, Sean Carroll here talks about dimension to someone who has no idea of what is dimension, no formal definition, to someone who is like a theoretical physicist. And you can see in these videos that are in different topics how people kind of change the language they use to teach people. And most of people who have been chosen for these are people who are really good at that. So it's not only Feynman who could do it. Apparently, other people can do it to a, well, smaller extent, but still, it is something that people can learn. So, so apparently, there are some other issues. Another issue with science communication is that it's a lossy process, meaning that when one expert tells to someone who knows less, and it goes on and goes on, at every step, something is like faded away. And to give you a very good example, I want you to think about the concept of entropy and the second law of thermodynamics. I have heard it many times that entropy means disorder. And the second law of thermodynamics implies that disorder is always increasing in the world. This is not the case. We all know that entropy does not necessarily mean disorder. And the second law of thermodynamics is quantifiable, and it should be mentioned in a very rigorous way. So every time we teach other people, something is out, and it makes it a bit more difficult when we want to communicate some ideas, because sometimes we communicate something or we want to communicate some idea, but when it arrives to people, we have ruined the whole thing. There is this very famous story from Rumi that a guy goes to a tattoo artist and asks him or her to, hey, I want a tattoo on my shoulder. And when they start doing the tattoo, the guy starts feeling the pain. I say, okay, what part of the lion it is? I say, it's like the tail. I say, skip the tail. And then again, the pain is there, and the guy asks, what part of the lion is it? It's like, it's the head. And that's okay, skip the head. And at the end, Rumi says that the guy leaves the room with some like cherub on his hand, which doesn't mean anything. And most of the time, oversimplification in science communication does the same story that we just mentioned. A lot of people just talked about COVID, but they ruined it because they oversimplified it for people. Now, okay, all of this now makes sense when you think how bold these arrows can be. The darker the arrows means there are more people in that. So usually in all disciplines, like when you think about physics, there are some experts that they teach or like let other people know. And as you go to the left, the arrow gets bolder, meaning that there are more people who are doing this. So for example, at the school level, like high school level, there are so many physics teachers around the world. And then at the level that very random people in the street are aware of physics fact are less. So like the bolder means there are more people actively participating in that. And when you look at like a very new field of science, you see that yes, there are some experts, and then there are like some other experts teaching their graduate student, but nothing is there. And the question is that what is the case in network science, right? I mean, the whole introduction was to get here. And this is now where my contribution starts. So for sure, for popular science part, there are so many books, you know them, like the Peter has also a very nice blog post about all of the complex systems type of popular science book. And there are other new things like Quantum Magazine has done a nice job. There are a lot of podcasts on this. And then we have this type of things which are more formal. Like, for example, Mark Newman has his books on network, the old one, the new one. He has a survey on complex system. He has a very nice review article on message passing approaches. And I personally would always recommend anyone new in network science, hey, go and read Mark Newman. Okay, so from now on, I'm talking about science communication situation in network science. And most of people know Newman because of his paper and contributions for sure. But the thing is like that Mark Newman is one of those people who has done a marvelous job of doing science communication in our field. And I would always recommend anyone who is new in network science that go and read Mark Newman, either his books or his like review articles or like research papers. There are, of course, like online courses that kind of cover a lot of subjects in complex system or network science. There are like interesting modules to play with. One of them is like complexity explorables, that it has a lot of like interesting simulations or something that you can basically play with and gain a lot of intuition. And there are people who have dedicated their PhD time and they've written a very nice thesis. And I'm saying and advertising for this because I believe for us in network science, something that can really help people who are newcomers is that we should provide a nice text when we are writing a PhD thesis. And I believe it's a very hard task, and I believe that most people don't want to do it. But the point is that we are in a very new field of science, and if people who are just like writing their PhD thesis are not careful enough, then it would be harder days for newcomers. I believe a thesis should be in a way that when someone is looking at the paper, and think that, okay, I want to understand these papers, they should go back in the introduction and introductory chapters and gain enough knowledge so that they can really read the papers if they are like patient enough. And I believe this is something that nobody talks about in our field. Like some supervisors are just saying that nobody is gonna read your thesis, and that is the case because there are not enough good theses around. And there are other resources. For example, I have always enjoyed reading Peter Holmes' blog, which I would say they're as valuable as, for example, Mark Newman's, as some resources for everyone who is doing research in network science or complex systems. I recently interviewed Peter, and you can go and see the video. I have asked him a lot of questions regarding how he really do it and why he is doing it, and a lot of things like that. But the question, or the most important question, is that when you compare network science to, let's say, physics, there is a huge bug or a huge gap, and that is that we have enough books for popular science part. We have good papers, we have good reviews, but this part, which has to do with graduate schools and educating people at university, is really lacking. You may argue, for example, that recently Santa Fe Institute has published this list of fundamental papers in complexity science, and you can always find this type of list. Even Peter Holme has a very nice list. But the thing is like that when I'm teaching physics to you, I always tell you, okay, go and read Weinberg. I never tell you that go and read like 100 papers from relativity and cosmology and blah, blah, blah. Yes, at some point a researcher should do it, but like going through this many papers is not an easy job. We really need to improve the classroom experience as the main part of science communication in network science. And I want to tell you a story which we have here. Like, it has now been 4 years that I'm TAing this course, which is like mathematical methods of network science. And every year I try to come up with new exercise sets for students because we want them to be new, because we want them to be engaging. And more importantly, we don't want a student to just copy paste answer from last year, right? But it's such a challenging task for me as a TA and as for Miko as a professor of the course, that coming up with new questions which are reasonable at that level is super hard. And every time I talk to people that, hey, please come and do a good book, write a good lecture on what you're teaching, they kind of avoid it because it's super hard. But the problem at hand is that a good textbook is not a good textbook that tells a good story only. A good textbook is a text that covers the concept and tells a story, but at the same time, they come up with really good questions and problem set at the end of each chapter. Now, I have a pile of network science books here. I don't want to show because I don't want to make my colleagues angry on something. But even the best of them, they do not come with good exercise sets. I know it's not doing like thermodynamics, but the problem is that most of the books have written in a way just to turn papers into books. And this is not enough educational material. I personally believe the most important issue for us at graduate school is that most of the papers are so technical and not related to our field or our research, but at the same time, we do not have really good courses here. And this problem should be done by community. But at the same time, there is this issue that teaching and writing a good textbook is not appreciated because there is no incentive in writing a good book, except it's fame or whatever. But a researcher on a regular basis is not motivated to any of these issues. And I believe one of the things that network science community should really go for is to come up with ways to fix this issue. Otherwise, in future, we will have generations of new network scientists who are not as deep as the professors because they grew up in a situation that learning was much harder than it was before. Because nowadays we have a pile of new things to learn, but not a pile of new material to use as a learning equipment. I hope I have made my point, but that is what I was going for. Thank you.
Thank you very much, Abbas. It was really nice, this talk from you. Everybody, someone want to comment? I have a comment actually. So I guess I can go on. So yeah, there is this gap in complex system that is kind of a new topic. So there are not many books on the general, for the general public. But I guess something is coming out in the last year. Probably yesterday, I was reading on Twitter that someone published a book for children explaining complex system. That there is an illustrated book on complex system. Of course, this is extreme.
Yeah.
But I mean, do you think that eventually this new field can be taught in school?
I mean that's a very different types of question that you can always argue what should we teach at pre-university. For example, these days a lot of arguments are that we shouldn't focus that much on calculus related mathematics. We should teach more statistics people because and I'm not really the right person to answer this question. When I was in Iran, I used to organize a lot of workshops for high school students so that I make them interested in complex systems in general. And we did a lot of simulations together. For example, we used not very advanced thing, but like using NetLogo or this type of thing so that people have a feeling that if you come to physics, you can finally do this as well. Because, well, there is no bachelors of complex systems as a popular field of study, right? So my task at that time was to make people to see more diverse picture as a physicist, what physicists can do other than just dealing with particles, right?
Yeah.
So for sure, you can always teach them, but that's a very different issue that what country or what education system really want to go for it. My main concern at the moment is people from the bachelor's to PhD level who are doing network science. I highly believe that there is no good course. And this is a bad claim because one may say, we had this very good course in our university. And all of these, they fade away, that if there is a good course somewhere, it's just only there. But like, for example, at the moment, there are so many good courses on quantum field theory, like very advanced quantum field theory, because it's a very old field. It has been established and people have committed a lot. And the main point is that in the physics culture, I personally believe one of the best things about the physics community is that people spend time in making teaching material. In other fields, it's apparently different. And in complex system, I'm not really sure if that culture exists. And that makes me worried, or not as good as in physics, for example. Did she just... We are eaten by Zoom today. Getting eaten.
She's away.
Okay.
Okay.
I guess it's getting so.
Okay. There's a comment from Gab in the chat.
Yeah.
We should have more tailored programs for graduates for network science, or is there hard for someone doing math or theoretical physics to get in network science? Yeah, this is kind of true because recently I have a student majoring in theoretical physics, and he wants to work with me about the network science project. So I can see the beginning is quite tricky although I guess he know the math and the math use is not very advanced, but I believe he know all of these, but still fitting into the context and trying to understand why we do this, or it's kind of tricky actually. I didn't realize before until I talked with this student. So
there is also this effect that, for example, when you talk to people who are senior enough, so when they came to network science, it was the early days of network science. So still they could kind of integrate with the new culture because the culture was very small and the topics and the questions. But now network science is like crazily big.
Yeah.
A friend of mine who is a good physicist was looking at my thesis and he said, your thesis is not a thesis. You have very simple formulas. You have two eigenvalues, no fancy linear algebra, no fancy field theory, no fancy, what type of a thesis it is? Because of course, the machinery that I was using was much simpler than someone used in a string theory. But the thing is like that when that guy starts reading it, it's like he had a lot of questions because like connecting these new concepts with the new frameworks is like not something people can really follow. And for our time, I guess it's even getting crazier and crazier. Of course, you can argue that the difference between network science and physics is that you get to physics, you learn quantum mechanics, and you learn quantum field theory 1, 2, 3. But in network science, because my research is so different from other network scientists, you may not need to do it. So maybe even the whole big picture is even a different, that every group has to come up with their own like courses, much more than what it is the culture in physics. That is true, but still, I believe there should be at least one good introductory books on network science, which come up with good exercises. I like, for example, Newman's book. I like it a lot. We teach it. I like it to the extent that I always say this is one of the best, but it doesn't come up with good exercises. And for example, there is another book from another mathematician, and it's not something you can use it as a textbook, And then there is Barabashi book. Barabashi is also very good, very engaging for people who are very new to the field. But it's very hard to, we also have another course that we use Barabashi as the main textbook, and most of the exercises come in Python. But that also takes a lot of time for us to maintain it because we need to come up with very nice questions. And learning happens through problem solving. And most of the lectures, most of summer schools, most of the events in network science are now just very mellow, sentimental type of course that there is a crash course, that there is no follow-up, One of the things that I liked from the physics of complex systems master course at ICTP in Trieste in Italy was that the courses, they have this spring school on complex systems, and every lecture was followed by TA sessions. And these days I have this feeling that people attend summer school just for fun, and most of the events which includes teaching are, the questions and problems are excluded, and I don't like it, to be honest.
Yeah. Also, on the good side, there is also the book from Vito Latora that is nice. He has problem as well. So thank you for the discussion and everything. I think we've done. It's
good. Sorry that it took this long. Yeah.
No, it's okay. Thank you very much, Abbas,
Thank you for having me.
And see you to the next seminar. Then in 2 weeks. Yes. We're gonna have Chick.
Bye-bye.
Okay. Bye-bye.
Thanks a lot. Bye.
Bye, Fra.